And what I will be talking about today in this lecture is some of the more recent research that we have undertaken in our research group that is on how to use production planning and control and schedules to look at the emissions that a construction site generates. So overall, the topic of CO₂ emission, energy consumption on construction and in construction is a hot topic here in Denmark and in Europe. Let me see if I can change the slides. 2 seconds. Just very briefly about me, not to spend so much time about it, but as I said, I'm a professor here in our department. I have a bachelor in civil engineering, and then later I took a Master of Science, a bit more in operation management, and then a PhD in construction management. That was at another university than Aalborg. It was, at Aalborg University, not here in Aarhus, and I've been here at Aarhus University in Denmark for the last 12 years. And more or less my entire career, I worked with production planning and control and lean aspects. And for many years, it was much about scheduling and productivity, quality and time. And in recent years, it's been more and more on green construction sites and how we can use lean principles to make construction more sustainable. And just so you know who is speaking, I just added a few photos of my everyday life outside the university, so you know, who is speaking. So a picture of my dog. I spend a lot of time with him. I have a old house that I'm renovating. I like to play a lot of darts, and of course, I also watch soccer with my 2 boys. So we spend time on that. Yeah, just so you know who I am. And as Dayana said, I'm situated here in Denmark, and of course you know where Denmark is. But anyway, I just put up this short introduction here that Denmark is a small country in the middle of Europe. They say it's the most happy country in Europe, so I hope that's correct. But a small country in the middle, maybe in the bit northern of Europe, so it's relatively cold here right now. And in zooming in on Denmark, Aarhus is situated here in the red mark in the center of Denmark. It's like 2-3 hours away from our capital, Copenhagen. And Copenhagen is the biggest city in Denmark, and then Aarhus is the second largest city in Denmark. And our campus is just in the middle of the city center. You can't really see and understand that, but I put a green dot up here in the upper left corner, which is the campus building where I'm sitting right now at the harbor front. And the main campus is marked with the red areas and extended recently with some of the more purple areas. So it's really a city campus. Yeah, so that was just to introduce myself and my department and where I'm from. And I will now move on to talk more about the topic of construction site emissions. And I put up here some numbers, and I know these numbers are from the Danish construction industry, but other reports say that they are very similar in other countries. So for instance, here in Denmark, we know that around 40% of all energy consumption that are used in Denmark is originated or is used in the built environment to construct buildings, to operate buildings. So it's 40%. We also have a big waste issue, especially from construction, where today we know that around 35% of all waste generated in Denmark and put onto landfills originates from the built environment. So we are by far the industry in society that generates the most waste. on a political agenda, there's so much focus on CO2 emissions due to the global warming, right? So a lot of what we do has to reduce the CO2 emissions. And estimates show also that around 20% of all the emissions, CO2 emissions in Denmark, is originating from the built environment, and maybe 10% of that is actually from construction and from materials, which is where we want to focus today on when we are doing construction activities on construction site. What kind of environmental footprint is we putting on the society, and how can we measure that, and how can we reduce that? So that was kind of to frame the situation. And putting that frame into a little bit of a historical perspective, then there has actually been a big change in how our energy has been used in construction. Because if you go back maybe 10 or 20 years, looking at this, what I could call a typical building here, when you then try to separate whether the energy is used for operation purpose or for what they call embodied, which means that are used for producing materials and constructing on site, then you could see that in history, most of the energy consumption were in the operation of buildings for heating, for cooling, for lighting, and so on. But today, the engineering design companies are so efficient in designing low energy consuming buildings, which they could here they call it high performance buildings. But anyway, designing buildings which has a very low operational energy footprint. But at the same time, there has been very little focus on reducing the embodied energy use. Here it says embodied carbon, but this is of course the carbon footprint that is arising due to an energy consumption. So we haven't really focused a lot on reducing our material, changing the type of material, reducing waste of materials, and so on. So more or less in Denmark, and I guess it's the same in most countries, we're still using the same materials. We're still using the same amount of materials. So it means that we are using way too much concrete, way too much steel, and way too much glass, for instance, which are all materials that are very energy intensive. So they have a big carbon footprint. And yeah, the most right is just to say that it's even possible today to construct what they call net zero energy buildings. So buildings that are not consuming any electricity or energy from the grid. It has solar panels on roof and so on. So it doesn't require any additional energy consumption for operation, but still we have the same embodied carbon footprint. And to give you a rough idea of how it has changed over time in Denmark, then it has actually reduced from maybe around 350 kilowatt hours per square meter per year for operational energy purpose down to 40 in average today. So it is more or less a factor of 10. But so that's just to frame it. But so the problem is here that we haven't really done anything about the embodied energy, the materials that we are using and wasting on construction sites. And to get that into the equation, it's not enough just to look at operations and how much energy we use in a daily operation. So we have to come up with a different framework. And this is typically the framework of the life cycle assessment, or LCA, right? So it's a framework you can use to calculate or evaluate, and maybe you can use that as a starting point to reduce the environmental impact of a product, or here it's typically a building's entire lifespan, right? So now we are interested in mapping the energy consumption from raw material extraction to making the materials, to installing them on site, to operating them, to do maintenance on them, and also at the end of life doing the disposal of these materials. So this is what we call a life cycle assessment. And the reason I'm putting that forward here is that that from this year, 2025, in Denmark, there's a new building code, a new building regulation that requires that all new build must do a life cycle assessment in order to get a building permit. And there are some thresholds on that, and one of the thresholds is related to construction site activities, which we will see a little bit later here. Trying to unfold a bit the life cycle analysis, and I don't know, honestly speaking, I'm not sure how much knowledge you have about life cycle assessment or how used you are to working with a life cycle assessment. So this may be purely reputation. But anyway, in a life cycle, we divide it into different stages. So we have what we call the A1 to A3 stage, which is production or extraction of raw material, the transportation of these materials to a manufacturer, and the producing of goods. It could be concrete, it could be wooden panels, it could be whatever type of material that we are later gonna build in our construction. And then we are approaching what is of interest to me, the construction site, because we have A4, the phase of A4, which is the transportation to construction site. And then the most interesting part, the phase A5, which is where we have our construction stage. This is the installation. This is all activities on construction site. Then at some point, a project is completed, it's handed over and starting operation. And then we have all what they call B1 throughout B5 stages, which is the use, the maintenance, the repair, the refurbishment, operation of energy, operation of water, and so on. So everything you do throughout the operation of the building. And eventually, we have an end of life stage of a building where you are deconstructing, demolishing the building, transporting the waste material away, and doing disposal of that. So this is the kind of the entire life cycle of a building. And today we are going to focus mainly on the phases A4 and A5, which of course is the one that is relevant when we are talking about construction management and engineering. So I tried here to illustrate a bit graphical what is a construction site. So I put that in the middle here, and put a box around it, and say what happens is that a lot of things is transported to the construction site. This is what they call the A4 phase. So this could be material, this could be labor that is transported to the construction site. It could be equipment that we transport to the construction site. And basically, it could also be energy, it could be fuel that we are transporting into the construction site. But then on the construction site, we have a lot of activities going on, construction activities, of course. And many of these are using energy. It could be for processing, for using machinery on the construction site. It is for lighting of the construction site, for electricity in our offices on construction site. At least in Denmark, it's also in the winter time for heating of construction sites and so on. So we have a lot of different sources of energy consumption on the construction site. And then we also generate some waste. It could be material waste, it could be soil waste and other types of waste, which we then have to transport away from the construction site again. So this is kind of our boundary condition here for construction management, and looking at how sustainable is a construction site and what environmental footprint will such a construction site generate. And as I mentioned, here in Denmark, we have a new building regulation from this year. 1st of July this year, so it has been enforced now for almost half a year. And I guess we are actually right now the first and maybe also yet the only country in the world that has a strict life cycle analysis requirement for construction phase A4 and A5. So today, in order to get a building permit, a project has to document that they are below a threshold value of 1.5 kilograms CO2 per square meter per year for construction activities, the A4, the A5 combined. Of course, when you put on regulatory threshold values, the industry, they start to listen, right? Because then now it's become super important for the industry that they can achieve these building permits. So now the industry has suddenly become very, very interested in construction site energy use and carbon footprint. But the problem is actually that we know very little about this energy use on A4 and A5. And the Danish government, when they launched this regulation of 1.5, they also said that this is their first attempt to regulate. They don't know whether that 1.5 is a strong threshold value or an easy threshold value. They assume that some projects will have it easy to comply with the threshold, and others will have more difficulties. So, of course, as a research institution, one of our tasks is to investigate that further and create some knowledge around that. So, of course, we're doing a lot of research and some case studies. And here I just took some examples of a case study we have some master students that are doing right now. So they have been looking at different construction cases and trying to do the life cycle assessment of these cases, and specifically looking into A4 and A5, which is of interest to us, again, what's going on the construction side. And so this study here, which includes 10 case studies, you can see that the A4, A5 combined in this analysis is around 0.58 to 3.46 kilogram of CO2 per square meter per year. The average is 1.21, and as I said, the regulatory framework is 1.5. So you can see some projects are above, but many projects in this small case study is below the threshold value. If we try to dig a little bit deeper into what is the sources of this emissions on A5 and A4, then again it's only based on these 10 case studies. In this small study, we also have other studies, case studies that have numbers that are not totally identical, but showing the same trends. So what we see is that the energy used on construction site, meaning the fuel, electricity, and so on, used for machine, for operations, for cranes, for trucks, Manitous, whatever working on construction site, is around 70% of that footprint. 28% of that footprint originates for transportation to construction site, meaning delivery of materials from suppliers and vendors and so on. But the biggest problem in the life cycle assessment is the waste generated on construction sites. So this actually accumulates for maybe half of our footprint when we do a life cycle assessment. So for sure, there is some very interesting research to be looked at on how to reduce construction waste, because it is a super big root cause for environmental footprint of our projects. And just to give you a little bit more information about the type of construction waste that we typically generate. So in Denmark, we generate around 5 million tons of construction waste. maybe that number is a bit difficult to put into context, but it is more or less equivalent to 70 kilogram of waste per square meter of new build you construct. So think about it in this way, that if you are constructing a house or an apartment of 100 square meter, you generate 7 tons of waste. So that's a lot. And that waste, what is it consisting of? A lot of it is concrete, a lot of it is mixed, asphalt, etc., metals, and so on. So this tells us a little bit about the type of waste, and then we have good statistics in Denmark for what we do with the waste. Some of it is burned, and that burning process, of course, generates electricity and heat. Some of it is being recycled, but most of it is actually being downcycled. So this is, for instance, concrete that are being crushed and used for road work. This is a type of downcycling. And 6% even ends on landfill, where it isn't being used for anything. So this was the kind of background of the energy consumption, to giving you a little bit of update. And one of the things that we have been looking into in that context is this question of how do we actually monitor how much emissions and how much energy there is on the construction side. And this, as you will see in a minute, is actually quite complicated to get a very precise and exact number of what is the energy used on the construction side, because it has so many different sources. And we were thinking about, in this project here, you can see a lot of names and a lot of partners, and I'm only part of it. But that was one research project where we had this idea of, since it's so complicated to identify and assess all the energy consumption, maybe we could make a rough estimate by a more production planning and control perspective, by only extracting data from schedules. So this was the target of this project, to see how much energy data can we actually extract from construction schedules. So again, to show you the challenge here, again, this is the construction side. As I mentioned before, we have a lot of things coming into the construction side, which is materials, equipment, labor, energy, and so on, and something coming out of it. And again, we know that the carbon footprint of construction is too large. We have this new regulatory threshold, and a client and a contractor now of course have to document this threshold, document that they are below this threshold in order to get the building permit. So how do they actually get the data? I mean, that's a big concern for many contractors now. And to get the data is something about how do we actually monitor our energy consumption on the construction side? What type of sensors or what type of data are we using to monitor our energy consumption? And then, of course, there is also a big question of how do we actually reduce the energy consumption, right, if we are above the threshold? So generally speaking, there are different methods of collecting that type of data. So one method could be to use IoT, use different technologies, different sensors. You could put sensors on your power, your electricity. You could put sensors on moving equipment. You can have computer vision monitoring waste disposal and stuff like that. So there's a lot of technology possibilities to use IoT to get that data. But the problem is that the construction industry is not yet very used to use a lot of IoT, right? So when you come to a contractor and talk about sensors and monitoring, they are a bit scared about that. So another approach to get data is to do data mining on everything that is being transported into the construction site. So we can monitor invoices, for instance, or track delivery times and delivery quantities. We have quantities of bills and so on. So we can do a lot of data mining in systems and in papers on what has been delivered, and then we can try to associate that to energy on the construction side. And there's a lot of research projects going on right now. We have some of them here in our department. We have Jonathan who's doing some, and I guess also larger EU project is trying to look on that. But in this small research, our starting point was that this is a little bit complicated, all this technology and data mining. So would there be a more easy way to get the data, maybe not as precise, but as a rough estimate? So here comes the idea that we have been working on in this research project, and that is that, well, we know that all construction sites have a schedule. And for sure, you have probably seen many different schedules, and you know that they come in different qualities, and different level of details. Some of the schedules is very detailed, and these are good for this purpose. If you have schedules that are not very detailed, they're not very good for this purpose of estimating construction site emissions. But if you have a schedule like shown here, a takt time schedule, where you have it divided into different zones and different activities, you have the different takt times, zones, and so on, it's actually possible to get a lot of detailed information about activities, durations, processes, and resources. And if we import some, let's say, more generic energy consumption tables, meaning that we do not know exactly what type of excavator is used or what type of crane that is on this construction site, but we know the type of activity and we know it requires a crane or a truck or an excavator or whatever. Then if we use generic data for that, we should be able to do some estimation. And I really have to underline the word an estimate, right? So when you do estimation, it's not about being very, very precise on 2 digits, right? It's about delivering an estimate that is a rough number on what direction are we in. So that was the main purpose of this project, to see if we can succeed in extracting that type of data from the schedules, if we can have these different types of support tables. And we use that for documentation purpose. This is called, in Europe, it's called ESG reporting, where you have to report energy consumption per construction site. And you have to report that also for the building permit, as mentioned. So that was the main purpose. And then we had a secondary purpose, which is associated with this strange thing that when you are applying for a building permit, it is before you do any construction site activities. So it's based on a scenario, meaning that we think when we're going to do the construction, we will have this environmental footprint, because the building permit is always given before you start on the construction site. And now in Denmark, you have to show that the construction activities are below this threshold of 1.5. But then as a construction manager with a lot of experience from construction sites, and probably you have the same experience, you know that these construction sites, they are very dynamic. A lot of things always happens on construction sites. We have delays, we have machinery breakdown, we have manning up, manning down of labor. There's a lot of things going on. So we can kind of assume that the real life scenario will always be different than the estimated scenario, which you actually got the building permit based on that. So we also had this secondary purpose of being able to simulate different scenarios, like what if we do something, how much will our construction site footprint change if we have delays, if we use different equipment, and so on and so forth. Yeah. So what we did in this project was a case-based project. So we had a number of cases which were already finished, and we had all the detailed schedules and activities in the schedules based on that. And then we were trying to build up a number of different equations to track out, or not track, but extract out that data, that energy data from the activities in the construction site. And one part of it is to extract energy data that is related to electricity. That's actually the most easy part, because it's quite easy to monitor electricity consumption. So heating, drying, lighting, processing. This is what we did here. And later we added the equations and the data extraction for all moving machinery. But the step one was to do it on electricity. And we did it on these 3 different types of cases, as you can see here. And so one of the cases were a housing, a 9,000 square meter housing project. And looking only at the electricity consumption, now that we have connected all the data in our software, in our scheduling software, we have the supporting tables, we have everything, then we could play around, with different scenarios. So for instance, we could have a scenario where we have lights, turned on lights 24/7 in all areas of the construction site, and we are heating all parts of the construction site because it's wintertime in Denmark. Then we could have a scenario 2 where we only heat and have lighting when we have activities in the different zones. So we know that because we have the takt time planning, so we know at which zones we have activities. And we could have a scenario where we say, what if we do not heat the construction site? And here you can see the CO2 emission only as indexed numbers, but you can see that it's actually possible to very drastically change, or the outcome is very different, from the different scenarios. It's like a 69–70% difference in the different scenarios of how much CO2 that activity generates. So it is very dynamic. In the second project, which was a university campus building with some offices and some labs for bio, I think it was biochemistry or something like that. That project ended with a 12-month delay. So we had the data on that. And then we tried to simulate, what if they didn't end up with a 12-month delay? What if they have managed to only end with a 3-month delay? And if they had succeeded in that, that would have generated 14% less CO2 on the construction site. And that's because it has less production hours with heating, lighting, and so on, and processing. Yeah, and it's more or less the same with this last case study in step 1, only looking at electricity. This was a hospital. And here you can also see we have different scenarios, and it's again up to 42% change in the CO2 emissions. Then eventually we managed to include all the data on machinery and manpower moving around on construction sites, which is the more tricky part to get data on. We did that on a case study here, on a housing case study. We had the original schedule. We had a scenario where we had low manpower and machines, so we had longer construction time. And we had a scenario where we were trying to double the manpower to shorten the duration. Again, just to simulate different scenarios and then see the outcome in terms of CO2 emissions. And these were the results of that project. So you can see that it varies from 0.43 to 0.63 kilograms CO2 per square meter per year, which is nicely below the threshold. But remember that this doesn't include all the construction site waste. So that comes on top of it. So that was more or less the idea of this project, to see if it is possible to estimate construction site emissions based only on our schedules. And to try to conclude on that, then yes, it is possible to estimate that. And again, I have underlined or put in bold here the estimate part, because in these different cases, we didn't do the as is situation understood in that way. We didn't go out and measure if that number we calculated actually were exactly correct. We didn't track the construction site energy consumption for this project. We only simulated it on our schedules, based on our schedules. So the question is, how precise is these estimates? This is one of the questions that we're looking into right now. And when you want to answer a question of how precise is the data, you should also have the question in mind, how precise do they actually need to be? And especially taking into account that we now for sure know, because we have demonstrated it, that the construction site emissions are very dependent on the dynamic conditions that happens during construction, delays, change of manpower, change of equipment, and so on. All that are decisions that are taken after the building permit. So the question is, how precise do we actually need to be in order to get the building permit? Because we know that that number is very dynamic nonetheless. Yeah, so as I mentioned here, the actual emission can easily vary from the estimation based on delays, change in equipment, change or whether you try to optimize your construction site schedule to reduce CO₂ emissions, or if you do not try to optimize it at all. And from a regulatory perspective, the question also arises what to do about it. I mean, what will the municipality, our authorities, what will they do if they discover a construction project that received a building permit because the simulations of construction site activities were below 1.5, but then they started on construction. The construction phase started, and a lot of change occurred. They took out all the new machinery, putting in old machinery that is using a lot of fuel and so on. They were having a lot of delays because there was a lot of risk and uncertainty in the project and so on. And maybe at the end of the day, they ended up with a number that is way above threshold, maybe 2.5, maybe 3, whoever knows. What would you do about it? I mean, because you can't change it anymore. You already had all the emissions. You had all the electricity consumption. Everything did take place. So you can't take it out of our global system, of our Earth system again. The emissions did happen. So what can you do? Of course, you can penalize the contractor and the client by giving, economical consequences, but you can't do anything about it for the environment because it just happened, right? So these are some of the more political issues that are a bit difficult for us to work with. And here, just the last a small graphic is just a reminder of what I showed you a bit earlier, that all data that is generated in Denmark right now points towards that managing construction waste is the most urgent issue of a life cycle perspective of construction site emissions. We really have to reduce our waste and of course, especially our use of virgin materials, that's even more critical. Here it's just waste. It could be waste of reused materials and so on. But of course, a lot of that waste is waste of virgin materials, and that is highly critical for our life cycle. It's highly critical for our emissions, and it's highly critical for our resource, what do you call it? The amount of resources that we actually have in our Earth. So, for instance, here in Denmark, they're already talking about that there is a lack of gravel. As one example, they are now talking that we will soon have a lack of biomaterials, so a lack of timber. So it doesn't really help us that we are wasting so much material on the construction side.